Hey gang, welcome back to Geo2. This will be the second part of the plate tectonics lecture. So we finished this on Wednesday, or I suppose it was Monday the 14th. Um, and yeah, this wraps up the material that'll be on exam 2, which we'll be taking next Wednesday, the 23rd. So we'll get into it. Last lecture, we sort of left off talking about this guy here, Harry Hess, and his idea of seafloor spreading, which he proposed in the 60s based on observations of variable depths of the seafloor primarily. He observed that there were these very shallow mountain range looking features in the centers of ocean basins, and there were very deep trenches that were on the sides of several ocean basins. And he put those two notions together along with this idea of convection in the mantle, and he proposed that the seafloor it spreads from a central ridge where new seafloor is created. That you can see here in this schematic. There's a central ridge where new basaltic ocean crust is being created, and that crust is then moved laterally to either side, where it ages and cools, becomes denser, and eventually it becomes dense enough that it can be subducted back into the mantle, potentially, in these subduction zones where the trenches are, as that says there. And so this was a major step forward. It sort of took Alfred Wegener and Arthur Holmes's ideas and put them together, at least with respect to the seafloor. He didn't really say much initially about continents moving, but this was sort of joined together with, well, I think it's really it's a few more slides down, but it was joined together with continental drift several years later, and this sort of modern notion of plate tectonics was born. We talked a bit about the initial evidence for seafloor spreading. It came initially in the form of this magnetic polarity reversal, and the history of magnetic polarity reversals of the Earth as a whole. They can be recorded in iron-bearing minerals that can have magnetic properties in and of themselves, and because of that, they can record the magnetic field that the Earth is existing within when that mineral cools from a molten state, or if it's heated above a certain temperature. Remember that temperature is called the Curie point, named for Pierre Curie, Marie's husband. In any case, that was sort of the initial evidence for seafloor spreading. And this is a 75 million year record here on the right, showing magnetic polarity reversals. The dark bands represent what we would refer to as normal polarity, and that's north at the north. So that's what we're in today, is normal polarity, but it's reversed back and forth throughout Earth's history. And it does so in a pretty irregular fashion. It's not like every million years it flips, but it does so more or less, on about a million year time scale. If you look here, the last time we were in reverse polarity stably was about 1 million years ago. And then you get, 2.5 million years, you get back into the next normal epoch, and so forth. Okay, and so the real evidence here that was published by this group, these two authors, Vine and Matthews, was really the recording of those magnetic polarity reversals as alternating stripes on the seafloor that run parallel to the ridge where new crust is being created, and this hypothesis that should be true carries with it this prediction that there should be symmetry about the ridge axis, because if new material is created in the middle and then it spreads in both directions, then those reversals, that history of reversals, should be preserved on both sides, right? And so we would expect the ocean floor to look something like this with respect to magnetism. You have a ridge axis where new crust is being created, and that new crust is very hot, and as it cools, like almost all Earth materials, as it cools, it becomes denser, more dense. And so as it becomes more dense, it sinks down and sits a bit lower. And so these central ridge axis regions are high, topographically high, because the crust is very hot and very low density. Okay. And so that kind of took us, I think this is where we left off, with the age of the seafloor, and so I think I said last time that that major coordinated international efforts have been been carried out to sample the seafloor in a systematic way. And so for many decades now, the International Oceanic Drilling Program and other previous iterations of that program have been operating scientific drilling throughout the world's oceans for a variety of purposes. One of the sort of fundamental things that they do with every core they take is they date any material that they can. And so if you get down to the actual ocean crust beneath the sediments, and you date the age of the igneous rock, what you find is that on the ridge axis, this is the East Pacific Rise, or along the Mid-Atlantic Ridge, the rocks are really young, 1 million years, 2 million years, 3 million years. As you move away from that ridge axis in either direction, the rocks get older, right? You can see from this that the East Pacific Rise is actually spreading much faster than the Mid-Atlantic Ridge, right? That's true for a variety of reasons, but it's just empirically true if you look at this figure, right? All right, and why that's true, it's a complex question, but at the first order, it has a lot to do with the boundaries that these plates share with their neighbors. Okay. And so, again, in the late 60s, continental drift and seafloor spreading were united into a single unifying theory of plate tectonics. And that is to say that the lithosphere, which is the uppermost portion of the Earth, it's rigid, so it's not capable of this type of convective flow like we're talking about in the upper mantle. The lithosphere, specifically, it contains the crust, but it also contains a thick portion of the uppermost mantle that's rigid. It's above the asthenosphere, which is that region where convective flow is possible, but it does not convect. It's rigid, and it rides along with the crust. Okay, that's called the lithosphere. Now, the lithosphere is broken up into about a dozen large plates. If you count the little small fragments, it's maybe 2 dozen, but not much more than that. These plates, these individual plates, can contain ocean floor, continental crust. This should just say ocean crust, continental crust, or some combination of both. Okay, and these two types of crust are compositionally different. I think we've alluded at least to this fact previously, but continental crust is made up of felsic minerals. That is to say that they're minerals that are rich in feldspars, or rocks really, that are rich in feldspars and quartz, or silica. That's very different than ocean crust, which is what we would call mafic in composition, and that is to say it's a chemical term. It means that it's rich in iron and magnesium. And as a result of those chemical differences, the rocks that are made up of those elements, really that chemical soup, the rock type out here in ocean crust is basalt, and that's pretty dense. It has a pretty high density, especially when compared to continental crust, which is largely granite and andesite, much more felsic rock types that are much lower density. And so as a consequence of that, a direct consequence, continental crust is never really subducted. You can never really force continental crust back into the subsurface. It just kind of accumulates. And that has a direct relationship to this here. The oldest ocean floor that we see, the oldest ocean crust, is about 200 million years, maybe 220 million years, out here kind of off the coast of Africa, I think is the oldest. But don't quote me on that, but 200 or 225 million years is about as old as you're going to find. That is in stark contrast to continental rocks, which some rocks up here in the Canadian Shield are well over 2 billion years old. Some rocks up here in Greenland are over 3 billion years old. Many rocks down here in Australia are well into the billions of years old. So that's really different, right? Why is there not really old ocean crust, but there is really old continental crust? Well, the answer is because the density is different, and ocean crust is dense enough that it can be forced back into the Earth's interior, whereas continental crust is not. It's like taking a balloon and trying to put it underwater. It'll just come right back to the top. And so continental crust accumulates. It has accumulated throughout Earth's history, and it forms these thick piles. Continental crust can be it can be on average about 35 kilometers thick. It can be up to 70 kilometers thick, whereas ocean crust is pretty uniform at about 5 kilometers thickness. So that's very different, right? Very different. Has a lot to do with why the oceans are where they are, right? And why there's land where there is. It's really because of that. Okay, so the Earth is broken up into these plates. This is a map of the world, obviously, that shows the plates, at least the major ones. And you can see there are some big ones, like this Pacific plate here. There are some little ones, this Philippine plate or the Fiji plate. There's a very small one up here, the Juan de Fuca plate. But what we're really focused on here is these boundaries, right? The plates themselves are pretty stable. You can see here that the African plate, for example, contains a large amount of continental crust, Africa, but it also contains a bunch of oceanic crust. And so this coast of Africa here, we would refer to as a passive margin, right? It's a continental margin where the continent meets the ocean, but it's not a plate boundary. So it's a passive margin. The same is true of the east coast of the United States or of North America. It's a passive margin, transitions from continent to ocean without crossing a plate boundary. Right? The west coast of the Americas is not. It's an active margin all the way down. And in fact, the Pacific is generally rimmed by active margins. Okay, and that's important. Right? Oops, where are we? Okay, it's important for a bunch of reasons, but it has direct implications for things that we observe at the surface. Right? So this is the distribution of earthquakes, and as you can see, if we put that next to this map of plates where the continents are in the same spots, there's North America, you can see that the earthquakes almost exclusively follow these plate boundaries, right? Very, very concentrated along plate boundaries. You can see that there are some places where they occur off plate boundaries, like there are some earthquakes out in the eastern United States, but not many at all. Most of them occur on plate boundaries. And you can see that even these divergent plate boundaries, like the mid-ocean ridges, they create earthquakes as well, right? Through that activity. Volcanoes are a very similar story. They're concentrated at plate boundaries. However, they're concentrated at a specific type of plate boundary, right? There are volcanoes associated with both convergent and divergent plate boundaries. But there are generally not volcanoes associated with transform plate boundaries, and most of the divergent plate boundaries are underwater, right? So we don't see that volcanism. It's still there. Mid-ocean ridges are essentially a continuous string of volcanoes all the way down. The mid-Atlantic ridge is essentially a 5,000 mile long. Or more, probably 8,000 mile long volcano, effectively, right? Same thing with the East Pacific Rise, but they're underwater, so we don't really see them. Occasionally, there are places where the mid-ocean ridge comes up above the surface, and that's related to very specific conditions, like is true here in Iceland. This is really an example of a hot spot, which we'll talk about momentarily, underneath a mid-ocean ridge, and that resulted in this massive pileup of basaltic material that created the island of Iceland. Okay, and so it says down here, this ring of fire is a term that people use to refer to this, the margin of the Pacific plate, or just the rim of the Pacific all the way around. That's because it's rimmed by volcanoes, and there's a reason for that. This is seafloor bathymetry. So bathymetry, again, just refers to the depth beneath the surface of water. So it's like a topographic map on land, but it's for underwater. So bathymetry is just a measurement of depth. And if you go out and you measure the depth of the ocean everywhere, you get an image that looks like this. These ridges in the centers of the ocean basins are topographic highs. They're like mountain ranges. And these very dark kind of rims or bands along the edges are subduction zones. Those are trenches. And so to give you an idea, mid-ocean ridges, the ridge might be around 3,000 meters depth. The ocean floor out here, away from the ridge, might be around 5,000 meters deep. And these trenches, the deepest trenches, like the Marianas Trench, these really deep trenches in here, they can get down to over 10,000 meters, I believe, or something in that neighborhood at least. So, so it's a very heterogeneous distribution of seafloor when it comes to how high it sits, and that's an interesting observation, right? I don't know if Harry Hess was the first person to make that observation, but he was certainly the first person to put it together with this idea of convection and upwelling of hot material at the ridge axis and downwelling of cool material in these trenches, right? Okay, so there are three different scenarios that could occur when we take two things and put them next to each other. They could, assuming that they're not just sitting there stable, which none of them are, they're all moving to some extent. There's stress. There's a stress field, right? That is regional, and it causes strain. It causes motion. And so there are basically three things that can happen here. The two plates at the boundary, they can be moving away from one another. That's divergent. Okay, diverge means move away. So it could be a divergent boundary where the two plates move away from each other, effectively creating a void space in between, right? Which obviously the Earth isn't going to like very much. You can have a convergent boundary where two things are coming together, right? Like a car accident. And in that case, one of two things is basically going to happen. They're either going to crumple up, right, like that, or one is going to get forced underneath the other, right? And either one can happen. It has to do with the material and even more specifically the age of the material that is butting up against each other. And we'll talk about that briefly, or we'll talk about that in a moment. Transform boundaries are the third type. Those are boundaries like we have here in Southern California in the San Andreas Fault, which just slide past each other. They're not pushing into each other, they're not pulling apart, they're just sliding past each other. And those happen in a very specific place on the Earth, and we'll talk about that in a few moments. Okay. So, okay. So let's see, this is a picture over top of this, because I'm not in presentation mode here. So again, three types of boundaries. You can have divergent motion, where two plates move away from one another, creating a little trench in the middle and allowing for mantle material to come up to the surface and melt through decompression. Okay, it's decompressional melting, because the material in the mantle, you know, we talked about it being plastic in nature and having the ability to convect. And that implies a very specific state for a material. It's very hot, and it's so hot, in fact, that it would be a liquid, right? It should melt, but it doesn't melt because there's an enormous amount of pressure. There's tons of pressure because of gravity and all this overlying rock, essentially, that's pushing down. And so the mantle is under an enormous amount of confining pressure. And if you increase the pressure on something, the melting point goes up, all right? And so these materials are existing in a state where at surface pressure, so 1 atmosphere of pressure, they would be molten, they'd be liquid. Even at much, much higher pressures, they would still be liquid. But there's enough pressure down there to keep them a solid, all right? But what happens when you start pulling the crust apart in either direction is that you create this kind of void space here, and it lowers the pressure on this material below. And when that happens, that material starts to melt and it rises up to the surface, and then it solidifies and creates a new crust. All right, that's what happens at divergent boundaries. All right, and that characterizes all of the mid-ocean ridges and all the oceans for that matter, because there's a mid-ocean ridge in the middle of all of them. All right, convergent boundaries, type B here, are where two plates are coming together. In this case, these are two ocean plates. You can tell because one is subducting, and only ocean plates will ever subduct. But you can also tell because they're about the same thickness, right? And continental crust is much, much thicker than ocean crust. Okay, and so many things are associated with these subduction zones, and we'll talk about that in a little bit more detail in a moment. But the third type, again, is transform, where the plates are just sliding by one another. You can see in both of these, the convergent boundary and the transform boundary here, they're pointing out that there's many earthquakes, and that's true. Obviously, we have lots of earthquakes here in Southern California, originating from the San Andreas Fault system, and near convergent boundaries, subduction zones, there's lots and lots of earthquakes that are produced as this downgoing slab is exposed to increasing temperature and pressure on its way down. There's also, as it shows here, lots of volcanism associated with subduction. And that's because as this plate is subducted, as it's going down into the Earth's interior, it experiences pressure and temperature, and that causes it to, for certain phases, to begin to melt or to begin to release water that's bound in the minerals, and that water is buoyant for one thing, so it's going to move upward, and it also encourages additional melting just because of the material properties of those materials. And so there's always, with subduction, there's always this string of volcanoes or volcanism, magmatism, that exists parallel to the trench, just kind of behind it. And it's related directly to the angle of this downgoing slab, and when this slab experiences the correct pressure and temperature to begin to release water. That's really what it's all about. Okay, and so we have a term for this. It's called it's called an island arc, or a volcanic arc, or a magmatic arc, depending upon like what the scenario is. But you can imagine that if this is continental crust, say this is South America, and these are the Andes Mountains, a volcanic mountain chain, and this is the Nazca Plate subducting beneath South America, right? These are going to be mountains, as they are, the Andes, right? But say this is, say these are both oceanic plates, like exists in many places down in the Southwest Pacific. Maybe this is a sort of Indonesia, Java area, that area, Philippines. Those plates, they're oceanic plates, and they're running into each other. Okay, and when two oceanic plates run into each other, one will subduct because they're dense enough to get into the mantle. But which one will it be? Well, it'll generally be whichever one is older, right? Because as the crust ages, it cools down. It starts out very hot, and it cools progressively. And as it cools, the density increases until eventually it reaches a density that it's able to sink back down into the mantle. All right. Okay, so let's see. We did have this little picture here, and you can see quite a few things here, right? Here's a mid-ocean ridge, and crust is spreading in both directions. There's a continent here and a continent here, obviously very thick. They stick up above the water. This is a passive margin, right? As is that. As is that, for that matter, it transitions passively from continental crust to oceanic crust, right? This is another continent over here. This is an active margin, right? Because there is a plate boundary there, right? And there's this mantle convection that's pushing these slabs along, and then they eventually are, forced back down into the mantle and recycled. Okay, so specifically at convergent boundaries, like we said, we can have ocean-continent or ocean-ocean collisions, or we can have continent-continent collisions. If you have an ocean colliding with either a continent or another ocean plate, you end up with subduction because the oceanic crust is dense enough to be subducted. And that results in a deep ocean trench, this thing called an accretionary prism. That's basically just like sediments that are on, let's see, it's kind of like sediments that are chilling here as this slab goes down that get wedged up there. All right. You end up with a volcanic or magmatic arc, or if it's ocean against ocean, like is the case in we'll say Indonesia, you end up with an island arc, right? And so Indonesia is packed with volcanoes, right? These kind of arcuate chains of volcanoes that parallel subduction zones, but because it's ocean crust beneath ocean crust, those volcanoes produce islands, right? So we call it an island arc. All right. The difference between volcanism and magmatism, if you're wondering, is whether or not the molten material makes it to the surface. A volcano describes molten material erupting at the surface. Magmatism describes a scenario where that liquid molten material is coming to the surface, but it doesn't quite make it. and it kind of pools in the subsurface at some depth and then cools and solidifies there as a large singular body. Okay, and that might sound, like splitting hairs, but the Sierra Nevadas are an example. Really, all the rock around us, like box springs, are this very coarse-grained granite, granodiorite, something like that. That it's a very felsic rock, first of all, and it has really large grain size. That implies that it cooled very slowly at depth. It's all essentially one giant body of magmatic activity that was related to ancient subduction along the west coast of the United States. All right. When you have continents colliding with other continents, neither will subduct, and so what results generally is just a very large mountain range. All right, and so there are many examples of that. The most obvious is the collision of India with Eurasia. And so there used to be an ocean separating India, the Indian subcontinent, from Asia, and that ocean plate was subducting beneath Asia. And subduction progressed and progressed and progressed until eventually India came and just smashed into the side of it. But when that happens, the subduction stops because the continental crust can't be subducted. And so the downgoing oceanic plate just kind of breaks off and continues its way down into the mantle, and the colliding continental crust just comes together and kind of expands vertically. All right. We've talked quite a bit now about active versus passive continental margins. All right, so this is another example of a subduction zone, and in particular here we're looking at the distribution of earthquakes along this subduction zone, and what I can tell you is that this is right. They occur along the downgoing slab. Right, and this is a cross section, so it's just 2 dimensions. But if you projected this in 3 dimensions into and out of the screen, this would go from being a line into a plane, right? A 2-dimensional plane that follows the subduction zone, it follows the trench, and it has a similar angle going down. The earthquakes don't ever occur out here, they don't ever occur down here. They're all concentrated along the downgoing slab, which makes good sense because that's where they're coming from. But what I would tell you that's kind of interesting is that that this guy Benioff, he was on the faculty at Caltech, and I believe he invented the first seismometer, so an instrument to measure seismic activity, and he did so before plate tectonics was established. And so people were looking at these data and wondering why on earth this planar feature existed, this planar distribution of earthquake focus points existed, and they didn't have an explanation for it. It's called the Benioff zone. All right, that's the term for it, and it's, as it says here, a dipping planar or flat zone of earthquakes that is produced by the interaction of a downgoing oceanic crustal plate with the continental plate. Really, the interaction with the continental plate and then with the mantle. But yeah, there's all these earthquakes that follow it right down. And that made good sense once people understood plate tectonics, but like many things, right? If you go back to the land bridges and how paleontologists struggled to explain the distribution of fossils prior to the acceptance that plate tectonics exists and is real, and operates on long timescales, though it operates effectively. Until then, it was really difficult to explain, and people came up with crazy ideas like land bridges, right? I'm sure people came up with some crazy idea about why this existed, but it's why we refer to plate tectonics as kind of a grand unifying theory of the earth sciences, because it explains so much, so many important observations that are otherwise completely inexplicable. Okay, so ocean crust being subducted, earthquake foci, that's just the plural of focus. So a focus point of an earthquake is where it actually occurs in the subsurface. The epicenter is where that focus point would be projected on the surface if you just took it straight up to the surface, right? So the focus point would be here, the epicenter would be there. Okay. All right. So again, this is just another description of the same 3 types of boundaries. We have ocean crust being subducted beneath continental crust, leading to magmatism or volcanism. Right? You can have ocean crust subducting beneath ocean crust, in which case you're still going to get that volcanism or magmatism, but it's going to create islands rather than mountains, if you want to, split hairs there. If you do this could be an example of where India came into Eurasia, right? This would be India on this side, and we had ocean crust subducting for a while, but then the continent ran into the other continent, and it just sort of turned into this little mess of a crumpled up crust, and the oceanic plate breaks free and continues downward. Okay. All right. So there are several more of these cross-section diagrams. I can keep sort of repeating this, but they all sort of look the same, right? You're going to have an ocean in the middle with a mid-ocean ridge in the middle of that. Ocean crust is being created at the mid-ocean ridge. It's spreading in both directions. It could be a passive margin where it meets more continent, right? Or it could be an active margin, in which case the ocean crust will be subducted beneath. And with that active margin, or that subduction zone, will come a chain of volcanoes, mountains, right? Okay. So let's see, where are we? There we go. Here's yet another block diagram or cross-section diagram. I guess this is more of a block diagram. And so here we actually have a real distribution. We're looking at South America, like I mentioned earlier, and the Andes Mountains are a volcanic mountain chain that exists on the west coast of South America, down through Peru and Chile, and into Argentina, I suppose. You have the Pacific plate out here. You have a small plate called the Nazca plate here, but this side anyway, east of the East Pacific Rise, the plate is moving towards South America, and it's being subducted beneath, and it's creating volcanism, lots of earthquakes. You hear about large magnitude earthquakes in Peru and Chile. That's related to subduction. Also the volcanism in the Andes related to subduction. The fact that the Andes are there in the first place is a product of subduction. Over on the other side of the East Pacific Rise, you have the Pacific plate being subducted beneath the Australian plate, maybe the Philippine plate if we move to the north a bit. But that's subduction of ocean crust beneath ocean crust, and it creates these islands, right? That you can look around. It might be worth opening up Google Earth and just looking at the oceans. I mean, it's astonishing how you can see these features. And how much sense it makes if you understand the process of plate tectonics. Okay, and so again, we return to this, which is a map of all the major plates, and the boundary type is denoted here with either these lines with the little boxes on them, or these things, however you describe that. These are mid-ocean ridges. These are convergent plate boundaries. You could also just say this is a divergent boundary, and this is a convergent boundary, right? They've split this out. They say divergent. I'm not even sure what that word is there, but there are a few examples of divergent boundaries that are not mid-ocean ridges. Okay, and so like here's one of them, the East African Rift Zone. So that's not a mid-ocean ridge, but it's a divergent boundary. There's a lot of separation occurring there. Also in the Red Sea here, in between the Arabian Peninsula and Africa, there's a mid-ocean ridge that's very new. Okay, and so give it 10 or 50 million years, and this part, Somalia here, going basically right through Eritrea, you'll get divergence, and an ocean basin will form there. Given a few tens of millions of years from today. Somalia will basically just like rip off the side of Africa and kind of come down this direction. That is actively occurring, and there's lots of volcanism in the East African Rift Zone. There's also really, really deep lakes, Lake Victoria, very, very deep lakes. All right. So that third type of boundary, we've sort of covered convergent, divergent boundaries. The third type, again, was transform boundary, and that's what we have here in Southern California, right? The San Andreas Fault System. And it's really kind of interesting how this occurs. Transform boundaries truly occur all along mid-ocean ridges. You can see them. There are these little perpendicular lines that are found in there, and the reason that they exist is pretty simple actually to understand. If you think about a sphere and you have crust on a sphere, right? It's not a very good sphere, but you get the point. When I open my hands, right? If I spread that apart, it doesn't create the same width of opening everywhere, right? It opens more in the middle than at the ends, at the top and bottom. And that's true of the Earth. If you take the mid-Atlantic ridge and you say, well, we're going to open up the Atlantic Ocean, you spread it. As you do that, if you spread it at the same rate everywhere, then you would have a very distorted picture when you finished. If you want to spread it evenly and preserve sort of the architecture of the Earth, really, what ends up happening is that it spreads more more in the center and less as you move to the edges. And so to accommodate that differential spreading rate, you need these transform boundaries. And you can kind of see that here, right? Everything on this side of the boundary is moving toward North America here on the Juan de Fuca plate. But it's moving faster at one point. You know, the speed of motion, it's actually moving faster here than it is here. And you can tell it's moving faster here than there because the relative motion along this transform boundary or transform fault is that way. It's right lateral, okay? That one's going down, which means that this plate is moving this direction faster than this part of this plate, okay? At least that would be true if this extended all the way into there. Now, what ended up happening that created the San Andreas Fault system is that one of these sections of mid-ocean ridge was actually subducted beneath North America, and the transform boundary just sort of became the plate boundary until you get down here into the Gulf of California, where it becomes a mid-ocean ridge again. So this whole section here is a transform boundary now. There's only really one other place on the planet that I know of where there is a similar length transform boundary, and it's in New Zealand on the Alpine Fault system. Okay, so the final topic that we want to just briefly touch on is hotspot volcanism. And so hotspots are obviously a style of volcanism that is distinct from plate boundaries. It's not distinct from plate tectonics, but it's distinct from plate boundaries. And what hotspots are, most of you are probably aware, there's volcanism that doesn't occur at plate boundaries. Hawaii is a good example. You guys talked about this in your lab, so you're all aware of this. These are related to rising plumes of hot material that originate deep within the mantle. Okay, and where they come from is still an area of active research, but it looks like they might sort of result from the remnants of oceanic plates after they're subducted. They sit down there for a while and they get very hot, and then they come back up to the surface. Regardless of how they originate from deep within the mantle, and they're these kind of plume-shaped structures, almost like a little flame, that comes up to the surface, and it remains relatively stationary through time. We can identify these and image the geometry of them using seismic waves. And so we talked briefly last time about how seismic waves travel and the differences between P and S waves, primary and secondary waves, or compressional and shear waves. But beyond that, sort of the next layer of complexity there is that seismic waves travel at different velocities in different materials. And even more specifically, they travel at different velocities in the same material at different temperatures. Okay, and so if you make an assumption that the mantle is made of more or less homogeneous material, which is a fairly safe assumption to make, and there's a lot of evidence that backs that assumption up, then if you identify regions where seismic waves travel slower through the mantle, those correspond to hotter regions. Okay, and if you do this sort of tomographic imaging, what you find is that these plumes exist oftentimes beneath hotspots, more or less exclusively, really, or rifts, and it's a cause and effect. The hotspot volcanism is a result of the plume being there, right? And if a plume like that is underneath a continent, which occurs frequently, the continent will start to rift apart over time because continental crust is a very good insulator. And so heat will build up and build up and build up until, it starts kind of eroding the underside of the continental crust, and then the continental crust starts kind of thinning, and a new mid-ocean ridge is formed. And that's again what's happening in the East African Rift Zone. There is what's called the African Large Low Shear Velocity Province, the LLSVP, Large Low Shear Velocity Province, the African one, is this big plume of hot material originating deep within the mantle. Here, this will give you a kind of, it's this plume of material that originates very deep and rises up to the surface. This looks more like a little snake than a plume, but you get the point. It's rising up from very deep. And you guys did an exercise in your labs where you calculated the speed of the Pacific Plate based on the age of the rocks along the Hawaiian Islands and then the Emperor Seamounts, and then looked at the distances and the ages and converted it into plate velocity, which is a pretty cool little exercise, I think. Yeah. All right. So, we've come a little way from Alfred Wegener and his reconstruction, moving backwards, but we've learned that through paleomagnetism, workers are able to reconstruct the path that continents have taken throughout Earth's history, moving backward. And they can do that at very high resolution for a long time, certainly back to the early Paleozoic, so talking 500 million years ago or so, is a very, very, very robust record. And so most all of you, I'm sure, have heard of Pangaea, this supercontinent that existed in the late Paleozoic. But most of you have probably not heard of Rodinia, which was a supercontinent that existed before Pangaea. And so Rodinia was assembled at about something maybe 1.1 billion years ago, and it broke up about 750 million years ago. All right, and what I can tell you is that when it broke up, it really started breaking up at 717 million years ago. I know that because almost immediately the Earth was thrown into probably the most extreme climatic state that it has ever experienced. It was almost frozen solid. There was about a mile thick ice at the equator on continents. And that's pretty widely agreed upon. And that lasted for maybe 60 or 70 million years, from about 720 million years ago until about 640-ish, something like that. So quite a long time that the Earth was in this snowball Earth state. And most people that work on these things would agree that it was in one way or another directly tied to the breakup of Rodinia. That was what did it, the breakup of Rodinia. And actually some of my work, my research has been on actually the supercontinent before Rodinia, a supercontinent called Nuna, and the climatic implications of its breakup, which were, it turns out, really different than Rodinia. But I think we have an idea why, and it's an area of active research. But this was Rodinia, and when it broke up, a lot of things happened. And I think the last slide of this set, and the last thing before we jump into the material that'll be on exam 3, really the last two sets of PowerPoints that really focus on carbon cycling. We leave you with this, and that's that there is a general first order relationship between supercontinent breakup, seafloor spreading, sea level, carbon dioxide levels in the atmosphere, and as a result, global temperature. This is a topic that will emerge, like I said, in subsequent lectures. But I'll say right now that, what ends up happening, you put a supercontinent together, if you think about this, like right now, there's a mid-ocean ridge in the Atlantic, right? There are no subduction zones in the Atlantic. And so it's just going to keep spreading. The East Pacific rise is spreading really fast, like we said, but the crust just gets to the edge and then gets subducted. And so over time, the Pacific Ocean will shrink. It is shrinking, and the Atlantic Ocean is growing. And so, 100 million years or so from now, all of these continents might collide over here and create a supercontinent. And the Atlantic Ocean may take up half of the world. All right, now, if that occurs, what gets us out of that state? Okay, that's a really good question. And the answer is something that I actually kind of alluded to a moment ago, is that continental crust is a really effective insulator. And so if you put the continents all together like this, all clustered together, what ends up happening is that the Earth is just like this heat engine. It just produces heat through radioactive decay in its interior, and then it wants to equalize with outer space essentially because it's a system. It's a system, and there's a gradient, and it wants to equalize the force, the energy on that gradient. It's just like taking an iron bar and putting one end in the fire. The whole thing is going to end up being the same temperature eventually if you let it, right? Well, the Earth can never get there, at least not anytime soon. It'll take billions and billions of years before we reach like stable equilibrium with outer space. Okay, planets in the outer solar system are probably there, but the Earth, thankfully, is not. And it's not because we have tons of heat being generated through radioactive decay on the interior, and the Earth wants to get that heat out. All right, and so through that process, plate tectonics is generated. I mean, plate tectonics is the outward expression of the Earth's attempt to equalize energy with outer space, basically. And so if you put together a bunch of continents into a little group, they're a really effective insulator. It's like putting a styrofoam lid on the Earth, right? And so heat just builds up and builds up and builds up underneath this continental landmass until eventually it starts eroding the continental crust, and the continental crust starts spreading, and then it just starts erupting, and everything breaks up in spectacular fashion. And there are these enormous flood basalts, huge scale volcanism. And so like when Pangea broke up, there's what's called the Central Atlantic Magmatic Province, CAMP, CAMP for short. The CAMP volcanism was enormous. I mean, it had enormous climatic implications, global implications, and it went on for millions of years as this rift right here developed through the Cretaceous and earlier in the Mesozoic. And so that when those CAMP volcanoes erupted, it really it impacted, it perturbed oceanic and atmospheric chemistry. And so that's something that people have studied in enormous detail, the implications of that volcano or that volcanism. But if you go back here to the breakup of Rodinia, there was similar volcanism, probably much larger, in fact, and one in particular, the Franklin Large Igneous Province. It's up in northern Canada, and it appears as though the Franklin Large Igneous Province erupted at about 717 million years ago, and almost immediately the Earth was thrown into this snowball Earth climatic state. All right, and so why did that happen? Well, it happened because of the carbon cycle, more or less. All right, and so I've kind of kept kind of going back to this idea that like, well, how are we teaching this course? How am I teaching this course to you guys? Well, you want to understand the climate. And the climate is a complex thing, and there are a lot of different ways you can understand the climate. All right, but if you want to understand it at the most kind of fundamental level that still encompasses all of the necessary pieces, well, we need to understand, first of all, system science, right? Feedbacks and equilibrium states and residence times. Then we need to understand energy balance and the residence time of energy on the planet. We need to understand what controls the flow of energy in and the flow of energy out. And what we learned is that the sun gives us energy, and that's it. And the outflow is directly related, it's metered basically by the greenhouse composition of the atmosphere. That's what dictates how much infrared gets out of the planet's atmosphere and how fast. And so that has direct implications for the residence time of energy in the system. All right, and then we took that and we talked about the distribution of that energy specifically and how it affects air and water, right? And that's climate, right? Air and water are climate, and sunshine, I guess, or clouds, right? But that's air and water. So and that is climate. Where are deserts? Where are rainforests? Why? Where does the wind blow? Where does the wind blow, and why? Right? Those, it's not weather. Weather is like taking that to the highest order of complexity, talking about very local weather. But climate is really all about air and water and how it moves around. All right, and so we got to that point Now, if we want to understand what regulates climate on long time scales, we need to understand the carbon cycle, because really there are two greenhouse gases that run the circus here. It's water and CO2. And water, as we learned, is a feedback. You cannot independently control water. It depends on global temperature. And so the one that we can control, and it is controlled by the Earth and modulates global temperature over long time scales, is CO2. Now, right, we haven't talked a lot about the carbon cycle yet. Carbon obviously is involved in all kinds of stuff. We're built out of carbon, reduced carbon, it turns out. Limestone in the ocean is carbon, right? CO2 in the atmosphere, carbon. It's all over the place, and it cycles constantly. And some places, you can grow a fruit fly out of carbon and it'll be dead within a day. You can grow a human, you can grow a leaf out of carbon and it'll be dead in a season. You can grow a person, they'll be dead in 75, 100 years if you're lucky, right? Or you can form limestone that'll lock carbon dioxide up for millions, tens of millions, hundreds of millions. I have limestone in my office. I might have a piece sitting here on the desk. I don't know. It doesn't look like I actually do. I'm surprised that I don't have one. It'd be better if I could pick one up and say, we have limestone that's 3 billion years old, right? That limestone started as CO2 in the atmosphere, and it interacted with rocks chemically, and it was converted into carbonate, and then it interacted with calcium and magnesium in the ocean and formed calcium magnesium carbonate, dolomite. And that dolomite survived for billions of years. And so, there are lots of different aspects to the carbon cycle. There is tons of carbon, all right? But there's a very small amount in the atmosphere. And so because of that situation where carbon is cycled continuously, and there's a ton of it in the system, but only a little bit in the atmosphere, you can imagine that it gets cycled through the atmosphere really, really fast, especially if you include the biosphere. And you think about how much CO2 is drawn up seasonally into like leaf growth, and then all those leaves die and they decay and they're broken down by bacteria that convert that organic carbon back into CO2, and they gain energy from doing that. And so understanding how the Earth interacts, Earth materials interact with CO2 in the atmosphere, and understanding how biology interacts with CO2 in the atmosphere is sort of the final piece of understanding climate through time and the regulation of climate by the Earth, right? Because if, a lot of this discussion, a lot of the controversy surrounds whether or not these are natural processes, or these are unnatural processes. And I can tell you right now that they're human related. Like the rise in CO2 is obviously human related. You can demonstrate that using carbon isotopes very, very, very clearly. But you can't really make an educated conclusion or come to an educated conclusion about that question unless you understand the way the climate works and how the Earth regulates itself over time. And so that's where we're going to go, and but not until after the second exam. And so so good luck with that, guys. I'm gonna do a review on Wednesday in class, and I will I'll post a short review video online as well, probably in the afternoon on Wednesday. So thank you guys very much. See you soon.